complex nature of nitrosamines and its impact in two proposed sampling monitoring methods. This is developed in the emission and atmospheric metrology group at MPL in UK. I joined just 1 year back. I'm learning a lot from this new and exciting area, and we will discuss some interesting points. Amines had been used since the 1930s about, so it's a very old technology. It was used mainly in the gas and oil industry, but in the latest 80s, in the last century, MIT proposed to use that to counter-effect the global warming. And since then, evidently, there is a big interest in order to contribute to the net zero strategies. There were several, let's say, proposals, and we have to admit that the implementation was not as efficient as we thought 20 years back, but it is still growing, and should be growing because in order to become significant in comparison with the real requirements to achieve net zero as a strategy when we are moving towards a new energetic matrix. In spite of being a very old technology that now is being more modernized by using different kind of amines, still a lot of gaps of information and knowledge behind this that compromise the sampling methods and the metrology of this. And we will discuss some of them. This isn't a very economic, a cheap technology. The solvent can be easily regenerated. And in principle, if we don't have different chemicals around, you can obtain, let's say, a low degradation of these amines. But in real fact, what is happening is that they are relatively volatile, and then we have losses. And the main amines used and the secondary ones that are generated during the process are a potential hazard for the health and the environment. Among of these generated compounds are the nitrosamines. It's a whole family of different kind of molecules that are really, really difficult to handle with because they are carcinogenic, mutagenic, teratogenic, and they are potentially being emitted. So what we have a simple molecule like this one, for instance. This is the most used in the industry, methanolamine. And we have the exhaust gas with different compositions regarding the kind of combustible that we are using. And we have the solvent solution. But at the end, we end with a complex process in which we have low temperatures. It means we are below the dew point. So we have steam droplets that can transport, partially dissolved, partially like a gas, different kind of nitrosamines. This is the general structure. This is some of them. And then we have to sample that isokinetically, and we have these complex amines and nitrosamines going out there. Then our main problem is that there is not a standardized method for sampling, for capturing it and monitoring. And the partition between the gas and the dissolved phase is specific for each nitrosamine. Another problem that we're facing is that the first thing that we do is research in the literature. For instance, for this compound, we have all these different values for the solubility. Which one is the correct one? And we are talking about NIST, CRC, papers, data sheets, safety sheets. So there is a bunch of information that has been not centralized yet, and we are still struggling with this. Sorry. And then they are oily and sticky. It's possible that some new nitrosamines are formed within your sample also. And there are many other parameters affecting the evolution of the transport and the sampling that also have these kind of problems here. And for some kind of specific compounds, even there is not exist standards. Here in red color, we have some of the included in the priority list of the Environmental Agency in UK, and we did some tests. I will go to comment about this with these 8 nitrosamines using an EPI reference standard. For instance, if we plot here the flash point for one component, we can have 3 values, for instance. And if we plot 2 values, 3 values. And if we plot the boiling point, we have several options. So which one of all these options is the correct one? This is a good question. So fortunately, some work has been done before modeling and also compiling data. And in this work, for instance, they work with something like 4,000 different organic compounds and found that this empirical regression. What I did is we plot this empirical regression through here. Unfortunately, we can see that many of this data was there for wrong reasons that we can discuss later. There are many strange, interesting reasons. This is important to decide which kind of data are we going to use, even for modeling or for interpreting what is happening during our sampling processes. And not just because they relate with the vapor pressure, but also if we see the major part of the data on volatility is done at normal temperature, but the actual working point is around here, 80 to 120, and very few data is there. So we need this point to make a reasonable extra interpolation using the Antoine equation, for instance. And another problem that we have is the large variability of these parameters. We are talking about 5 orders of magnitude. Here I am just plotting the ones in the EPA standard that we used, but some of them are in the bottom of the list. And they are not going to behave equally. They probably cannot be sampled in the same manner. And so we are constructing a robust database on physical chemical data in order to be able to trust better in our modelings and interpretations. This is something very interesting. I just took the reference standard material certified uncertainty, and you can see that this makes a nice linear correlation with the volatility. It means that even for experts, the more volatile ones are more difficult to handle, and they have a larger variability. So this is a very important parameter. We have another complex situations here. Some of them are reactives, so we have to select which materials we're going to use. Some of them also are affected by parameters that we know that are really variable in the stacks. In the stacks, for instance, we can find sometimes 1 order of magnitude spikes of ammonia. And this means that probably nitrates are also varying. And we know that the rate of formation of nitrosamines scale with the square of these concentrations. So it is not really easy through an isokinetic sampling and this complex stuff to hold a continuous monitoring, but we will have some large variations in the rate of production. So some recent results that we have, I think that the main result is that we have established at MPL a bench test for testing the sampling methods. And we are trying to validate these two methods here, the liquid impingers and the dry cartridge for nitrosamines. So this process here is a testing at lab scale in this rig that we have developed. And we use control conditions and nitrosamine concentrations that we input here with different certified gases. So we can control all this and then evaluate what is the efficiency of the impingers. When we use impingers, we use 3 impingers, and at the end, at the very back, for 2 reasons, for safety and also in order to check that nothing is coming through, we attach also a dry cartridge. Okay, and this is done also in isokinetic sampling strategy. Some of our results with the impingers, because so far by the moment, the impingers is a better method for this kind of stuff, because in the case of dry cartridge, we have to dilute too much in comparison with the actual conditions of the stack, so the detection limits are going unpracticable. So the impinger recoveries are, we have still some issues in terms of the analytical methods that are marvelous for food, for pharmaceuticals and stuff, but apparently for this kind of studies, we have been observing, even in certified laboratories, some interesting biases. So we have an overestimation here for the impinger recoveries for the 5 more volatile nitrosamines. There are these ones here. You can see the values of the volatility. but not exactly 100%, 80% just for the 3 last ones in the bottom. So if we apply this criteria here that is often used, the last impinger recovery, just this passed here. But what happened, to be fair, these two just reach 80%. So we still have the question, because we know how much we are injecting. So this criteria as alone doesn't tell you the whole story. So can be also stuck somewhere. We will see that the ring type ones behave differently. So the impinger method with sulfamic acid to avoid the creation of new nitrosamines inside is the best available option so far by the moment in the tested condition, but it still needs to be validated. And for instance, this is the back cartridge that we add after the impingers. And it's interesting that what we obtain here correlates inversely with the vapor pressure. And it happened for all of them, all the linear ones, but not for the ring type ones. So it does not belong, that depends only in the volatility, but in the chemical structure. And it is possibly related with how sticky are these compounds. And so we can see that the ring type ones can be detected and the other ones are nicely correlated. So volatility is a key parameter, but again, the chemical structure will play a major role. In the future scenarios in the industry and also in the research, we know that a lot of kind of blends with different complex amines are going to be used. And the one that I was showing was just for monoethanolamine. So we will have a large family of a very varied composition with many, many species there. And we have to understand which kind of nitrosamines are we expecting, because I am completely agree with one of your sentences. We can't spot what we are not looking for. So we have to understand better what kind of complex situation we'll have. So we are making this paper in order to inform what we have found so far. It's very interesting how some very basic physicochemical aspects correlate with the findings that we have so far. And we are analyzing also our first tests in a real stack, okay? Using these methods. In the future work, we want to test different conditions, varying different parameters. So it implied a project much larger than what we did before. We are completely open to collaborate because we think that the rack that we have developed is answering many questions that will be easily solved in the lab before going to the stacks. We have to include other nitrosamines, as these two ones that have been measured in real stacks, but there are quite low volatile ones. And the method that I am showing, it can't be applied for them. So the problem with this is the possibility of condensation in surrounding areas, because they are probably being expelled from the stack in the water phase, in the droplets. But after they get in the atmosphere, probably they will be condensed nearby. Thank you for the UK Environmental Agency who support part of this work, and I will be very happy to take any question or comment you have. Gracias.